Okay, so it is Thursday, September 10th, and this is 522. And we are starting in on chapter 2 in the book. And then chapter 3 is mostly a review of regression principles. So we'll kind of review those relatively quickly. Chapter 2 kind of sets the basis for the entire book, and it doesn't treat everything in extensive detail. And it waits till later in the book before it kind of digs into these things a little bit. So it kind of sets the stage of where we're going. Now, in that respect, it's very important so it can help put other techniques into perspective. And the first idea we want to talk about is what the heck is statistical learning? Okay, what is learning? Now, as you've heard me say in the course so far, the verbiage, the words can be, quite misleading, or at least they can, in a sense, almost mask what might be going on underneath the scenes. So you can think of the objective of the course as we move forward is to look at the words, right? And in some cases, the words are actually quite fancy, right? Like statistical learning sounds pretty sophisticated, right? We're going to statistically learn. What does that mean? Well, you've got the surface layer, right? This is all the surface layer of statistical learning. And then you have the underlying layer. So you have the word that's being used, that's being bounced around, but actually underneath is what's really going on. Now, I guess it's an iceberg, right? It doesn't look like very much, but you can almost think of it like the iceberg, like the Freud analogy, right? That you have like the unconscious mind underneath the water and you have the conscious mind on top and things like that. It's not perfect, but it could actually help kind of clear this idea up a little bit. So today there's a lot of terms being bounced around, right? You have data science, you have machine learning and stuff like that. And when you think of things like support vector machines, they sound very, very complicated. And it sounds like there's a lot going on in the procedure. But our job, right? Our job is to find out what's going on and to look at this layer. Because we don't want to be just looking at words that sound nice, because that's, as I said regarding the Quan article, that's kind of where we get into trouble, is we think the word sounds good and then we derive a meaning from it, when actually underneath it's, what's going on is only this. So we have to get it down to the bare bone essentials of what the procedure is actually doing, what the statistics are doing, so that we don't potentially misuse it. And we can also see the unification among methodologies, right? And that's a big part of this, to see how do these methodologies unify based on basic principles. Okay. A couple of things here I just want to touch on. I just put a few notes. Is we also want to look at kind of like the pragmatic feel to all of this, right? It's very easy when you're doing statistical analysis and a lot of academic research for it to become kind of academic. And I don't mean that pejoratively, but you can almost make distinctions that really have no practical value, or it can be entirely misleading. Now, let me give you an example as we start. Cooking oil, okay, oil for cooking. I've been recently concerned with the actual fumes that could be emitted by cooking oil. I didn't know this before, but apparently if you heat cooking oil too long, it could actually emit carcinogens and things like that. And usually they say that the oil has to get about towards its smoke point, right? As the oil starts to smoke, there's actually chemicals and carcinogens that are released into the air. Right, not a very relaxing thought, right? You're cooking eggs and you're releasing carcinogens. Now, how many carcinogens or how many chemicals are actually being released in the air? They're not quite sure, but if you're smoking your oil and you're really like burning it, especially, they say that the number of chemicals increases, not only carcinogens, but other chemicals. So you typically want to keep your oil at a relatively low heat so you don't get it too hot, okay? But I looked into the issue over the summer. I looked into it and I started reading some reports on it. And of course, what are the reports going to have? They're going to have a lot of statistics and a lot of data analysis and stuff like that. So you look at this and they have something identified as oxidative stability. And my understanding is the oxidative stability is kind of like the time point before an oil starts to break down. So you're heating the oil, and at some point, the oil kind of the molecular structure of the oil starts to break down, and that's where you start to get the fumes up in the air. And apparently, you can't even see the fumes, right? So the oxidative stability of the oil is of great interest because you'd like to know when does it start to break down and avoid that breakdown point. Okay. So when you look at papers like this, they rated the different oils. Okay, so you had like olive oil, you had peanut oil, sunflower oil, etc. So what's the point of this discussion? Well, the point of this discussion is that in the different oils, they had oxidative stability here, and they had the different oils along this axis. And what happens is, I think they found that olive oil had some of the highest oxidative stability. So there's olive oil, and that rated pretty high. Then you had, I think peanut oil was actually pretty good. Don't cite me on this. And sunflower oil was just like awful. I mean, you have sunflower oil, you're supposedly going to poison your house. Okay, I'm saying that kind of jokingly, but sunflower oil apparently does not have very good oxidative stability, etc. And grapeseed oil is not that good either. So when you look at this and you look at the ranking, right? You look at the ranking, they're basically recommending that you cook with olive oil. That was the final recommendation. Well, if you're using sunflower oil, you shouldn't be cooking with it. That's what they're saying. But the problem is that if you look at data this way and you start to rank it, you start to do a raw ranking, well, the perception that someone takes away from the analysis is they throw out the sunflower oil and they simply restrict themselves to olive oil. So, oh, by the way, the study was published by an olive oil company, which we won't get into right now, but just so letting you know. But the problem is that even though the data are ranked this way, it doesn't necessarily mean you should switch to sunflower oil, okay? And when you look further into the paper, you see that the difference in oxidative stability between the olive oil and the sunflower oil is relatively small in terms of its practical value. In other words, and again, don't cite me on this exactly, but I remember looking at it, and olive oil took about like 6 hours or 5 hours before it started to break down at high heat. Like about 5 hours of cooking olive oil on the stove before it would actually start to break down. Sunflower oil, I don't know what it was, but let's say it was like about an hour. Okay, so 1 hour, and it took about 5 hours before it broke down. If you read the paper, you're left with the perception that you should use olive oil. But who cooks for an hour when you're cooking eggs, when you're cooking steak or something like that? Nobody, right? Unless you're doing that type of thing. Usually we fry something, it's relatively quickly. So the fact that this breaks down in an hour and this in 5 hours is really immaterial, even though this one was ranked last. Okay, even though this one was ranked last, it's really immaterial, and you should actually choose the oil that you actually prefer cooking with. Of course, they're not going to say that in the report. They're going to suggest you use olive oil. Why? Because who wouldn't want to use the oil with a higher oxidative stability? It's a better oil, right? That's what we think. But in terms of the practical appeal, you can choose whichever oil you want because you're not even hitting that 1 hour mark. That's an example of how the statistics that you read can actually be misleading or find differences that pragmatically it's not going to make a difference anyways. And I'm getting there to the concept a little bit of utility, okay? Utility. If the sunflower oil, if you really like sunflower oil, you should probably continue to use it because it's not going to make a difference. So we keep those things in mind as we go. And when you look at data, you always have to ask those questions. How much is the numerical abstraction actually distracting from the actual practical problem? Actually distracting from the problem of, the kind of like the real life problem, okay? Because otherwise you can really be misled. The other distinction I want to make before we start into this, is a distinction between music and science, okay? Now this is kind of powerful because I've been thinking about this lately. And the role of theory. I want to discuss the role of theory in this. There's music theory, and musicians out there will know what I'm talking about. You say, yeah, we know there's eighth notes and there's 4/4 time and all this stuff. There's music theory. Now, music theory does not um, tell you how to play the piano, right? It does not tell you how to play the piano. In other words, you can play the piano and you can violate every theoretical idea there is. What's the final judgment, right? What's the final judgment on whether you've played successfully, whether it sounds good, right? That's the final judgment. So if I played the piano and I violated the theory, say, you can't play that chord there, that's wrong theoretically. The response may be, who cares? It sounds good. And that's what happens with music. When you hear music presented in different ways, it actually, and you say, boy, that doesn't sound, that was like kind of offbeat, or that was kind of like a strange twist on those notes. They may be violating theory and principle, but it sounds good. The final verdict is, it sounds good. That's not the same with science and statistics. Now, with science, I mean, you can say if the drug works, the drug works. But when you're looking at statistical procedures applied to data, the theory governs first. There's no way out of it, right? So there's some things in statistics applied to science that you can't do, even if it kind of seems like a good idea. You can do that in music. I'm going to play these contrasting chords. It seems like a good idea and it sounds good. But in science, it's not going to work that way, especially if you're using statistical theory. In statistics applied to science, it's the theory that rules the day. It's the theory that rules the day. So if you're using like a cluster analysis or a different procedure, you have to be guided by the theory of how the procedure works, of how the method works. So you can run it, you can do the statistical procedure, but I see this all the time as well, as people violate the theoretical principle. Even though they're getting like a research result, they may be violating that theoretical principle. And you can't say at that point, what's the difference? It sounds good. It's not going to work that way because you're violating the theoretical principle. So you've got like theory up here and you've got practice down here. That's why the theory is so important, right? I'm trying to motivate a little bit why the theory that we discuss about these methods is so important. They're not two different things. It's not one is the practical, one is the theory. The theory informs the practical, or else it just doesn't work, okay? And that is really important to remember as we go through. So as we're looking at the different equations and the different symbolism and stuff like that, you have to remember that, you know, this is what's going to determine whether you're using it correctly. Because if you're not abiding by the theory, you're not using the procedure correctly. And even though you're producing an empirical result, it can be rejected based on not following the theory. So the theory is what drives us. I remember saying to someone one time, they say, why is the theory important? I said, because the theory is all we have in terms of applying statistical methodology. It's all we have. If you're not guided by the theory, you're kind of shooting in the dark a little bit in terms of applying statistical methods. Not quite the same in terms of just science, because with science, I mean, hey, if the drug works, who cares what the theory says? But a little bit different when you're talking about scientific methodology, okay, or a statistical methodology. Okay, a little bit of review here. So you got predictors, independent, dependent variables. I think we're all good there in terms of what those are. Input variables, output, and all that. Here's the example used in the book, many examples. There's like a least squares regression. So we're all okay there. Now, in general, we have the big idea here, which generalizes to almost everything in the book, is we have this idea of a function statement, right? Idea of function. Now, again, a lot going on here. You may look at that and say, I've seen that before, we know what that is. But you kind of look at it and you say, well, what are we actually doing here? Well, we have basically a systematic component here, and we have the random component here. Okay, so there's systematic and random information. Now, as we head towards psychometrics in the course a little bit, and we will be doing a little bit of psychometrics probably towards the end of October, getting into the other book a little bit. A big part of psychometrics and statistical methodology in general is accounting for the error term. Okay, so the error term is actually really, really important. And you're always thinking about this when you're modeling, right? When you're modeling, and we'll talk more about what modeling is, but you're always trying to get more of a systematic component than the error term. But you should be concerned about the error term, the unexplained variation. And the error term, I almost like to call it like the humility term, right? It's the error term that keeps you humble. Right? So, if you're doing a study and you're explaining 10% variance, well, yeah, that's only 10%, right? And there's a lot of variance unexplained. So, you want to tell your audience, you want to say, what, I did the study, but I'm explaining 10%. Most of what we know, we don't know. Okay. Give an example. I heard a researcher talk one time, and they were explaining like about 10% or 15% of the variance. And they opened the talk with saying, if you do this behavior, I know you will do this. I can predict you will do this, right? If you do X, I can predict you will do Y based on my study, which had an R squared of about 15%. That would be completely wrong, right? That would be completely wrong. Why? Because if I do X, if anything, what you've shown is that I probably won't do Y, right? I probably won't do Y. Why? Because you only have 15% variance explained. Even if that variance explained was 100%, but you didn't have proper controls and design issues, you still couldn't say that. So we got to be aware of that, right? We got to be aware of that simply because you're approaching it from the vantage point of what you've done, most of the variance is still unexplained. So the predictability is really often not there. You think of COVID, right? Well, you say, well, we have age as a predictor. Well, most of the stuff we still don't know, right? Well, if the variance explained is 0.15 or 0.20, that means most of it we're clueless about. So maybe age is partially in there, but most of it we don't know. So does that mean if you're 80 years old, you will suffer from COVID? Absolutely not. We don't know. Only some of it we know. So we have to be aware of that error term. We have to acknowledge it, and we have to be very honest about it when we're reporting our results as well. You never want to focus on only what you're finding. You want to focus on the science of it. And the science often keeps us humble in these cases. The function that connects the input variable to the output variable is generally unknown. So we don't know this function, and that's the goal, right? We want to know this function. You can see this is a rat, okay? The rat, running around in the maze or something like that. Well, maybe they have a pattern, right? You're trying to estimate the pattern. We don't know that pattern, but maybe if you have enough data and you observe the rat, you can find a pattern. But usually it's unknown, and that's what we're trying to estimate. That is the connect word, right? So F that connects the input variable to the output variable is generally unknown. Careful about the connect, okay? Careful about the connect. That's an equal sign, okay? Connect kind of has connotations of something more than just the equal sign. What they mean here is it's just associating. Again, that's an imperfect word, but it's kind of putting together that input and output variable. And this is raw mathematics, right? This is abstract mathematics. When you take this down to the scientific world, this matters, because if you use that word connects, the next question, right, coming up at your dissertation defense or your thesis defense, is going to be, how does that connect exactly? Well, in the mathematical sense, it's connection. In the physical sense, it may not be at all. Okay, so really, really important. When we overlay statistical methodology on physical phenomena or other phenomena, the properties of the statistical methodology in that abstract sense may not apply to the physical phenomena. And that's often an error that researchers will make, is they'll say, hey, the numbers say this, therefore, that must be true of the physical phenomena. Not so, not so, right? The difference between 3 versus 1 is a numerical difference that may not represent a difference in what you're actually measuring. Okay, and that's really important, that when you look, and remember, those are like interval ratio ideas, but when you overlay that abstract system, you don't know. I mean, you can even take silly examples like well, not silly, but more obvious, less obvious examples like weighing yourself, right? We see differences in weight. Maybe you're trying to drop a few pounds and you say, well, I've lost 5 pounds. Well, even that's a representation of the weight loss. We can be pretty sure that that represents a real difference in weight, right? The difference between like 200 pounds and 190 pounds, we can say that's a difference in actual weight substance. The numerical difference corresponds to the physical. But in social research, especially, social research is really, really hard. If you want to do an easy science, okay, go into like the physical sciences from that perspective, not from the perspective of learning organic chemistry, but from the perspective of actually dealing with physical objects. Those researchers, they don't have to deal with these issues that psychological researchers have to deal with, because they can just say there's a weight difference and everyone's like, okay, we get it. Psychological research is much harder in that respect because the numbers may not associate to differences on the physical object. Okay, that's a really, really important point. And it's a point that comes up at like thesis defenses and things like that, is how do you know that even corresponds? And if you don't know what corresponds, then you analyze all this data without even knowing what that scale actually represents. Okay, so beware of that. It's a good idea. Here's a fitting a model to data. So we've got errors around the line. This is a slightly nonlinear model. We know that the errors are positive, the errors are negative, and they're going to balance out. Overall, these errors have approximately a mean 0, while the expectation of the errors is equal to 0. So in the long run, the expectation, the theoretical expectation, is equal to 0. And that's a nice property to have in statistical models, because you might overestimate, you might underestimate, but hey, on average, we're gonna have 0 error. Well, that expectation, right? That expectation is in the long run. Okay, it's in the long run. So in the short run, we often we don't have that nice neat expectation, even though like in the least squares, the sum of squared errors will equal, the sum of errors will equal 0. The sum of squared errors will not if you have variation around the line. So what is statistical learning? It refers to a set of approaches for estimating f. It's for estimating the function. Okay. Why estimate f? Well, there's a couple reasons. The book divides it into prediction and inference. Usually they're the same thing, right? They're kind of combined into the same thing. Shouldn't say they're exactly the same, but we usually do them simultaneously, that we don't really have to worry about that. Now, inference, you're estimating parameters of the model. Prediction, you're using the regression equation or the discriminant analysis or what have you to make a prediction of future observations. So, in 521 in previous courses, you may not even heard that distinction, and that's okay. In the statistical learning environment, in the machine learning environment, et cetera, we often like to make that distinction because sometimes prediction is completely atheoretical. It's entirely atheoretical, and that's where we get this black box idea. Okay, so sometimes this function that we're estimating is treated as a black box. In other words, nobody cares what's in it. We just care if it works. We just care if it works. So oftentimes we don't care about the exact form, provided it yields predictions for y. Can you predict bank fraud? Can you predict credit card fraud? Yes, I can. I can predict when credit card fraud is going to occur. Well, then the bank says, really, how do you predict that? Doesn't matter. I can predict it. That's a black box idea. In the box, we may not even know what's going on. And this is seen actually in things like neural nets and stuff like that. They often actually don't even know what's going on with the inside the actual algorithm. They just care that it works. Okay? And that's perfectly okay. And this is actually kind of like a movement that's kind of where some methodology is going, especially you've heard of big data, the terms like data science, not quite so much, but some of this verbiage is associated with that idea, and it's been influenced by computer scientists and things like that, who are, in a sense, it's like the heck with the statistical theory. We just want to know if it like predicts this group or this group, and in some cases that's okay. But that could also be in like business, marketing, and stuff like that. Just give us the prediction. That's not okay in other respects. So there's a distinction here we need to make. That's not okay in many scientific respects. And let me give you an idea of what we're talking about here. Here I have the rat. I'll be referring to the rat a few times. Okay, so the rat is trying to exhibit choice behavior. I'm not a rat specialist, but I'm guessing that, well, you remember Tolman did studies on cognitive theory and all that stuff about whether the rat chooses and all that stuff in the maze. So let's say the rat starts here, and the rat could go this way, or the rat can go this way. Okay. Now, that's more than a black box, right? If you're a psychologist, an animal theorist, you are interested in the behavior of the rat, but you also want to explain the behavior. Knowing that the rat goes this way or goes this way is simply not enough, right? It's simply not enough. You want to actually know the process, or at least theorize on the process as to why it's going this way and why it's going that way. So this idea of estimating the function becomes important, but unpacking the function so that you get insight into this becomes even more important. And that is a little bit more along the lines of traditional mathematical modeling. Traditional mathematical modeling wants to know what the process is. It's a little bit different than the big data black box environment we see ourselves in some areas. So we need to be aware of those distinctions as we go. In both cases, we can say that there's statistical learning that's being taken place, but our job is to go, what the heck does that mean? What does statistical learning mean? What the heck does a statistic learn? Well, we got to see what all that means. Okay, so here's a regression surface. So we've got a more complicated surface over here. The red dots are values for, you can look through that, years of education here, seniority and income. Again, when you get into these higher dimensions, it's really hard to visualize. This one isn't so bad, but you got the two-dimensional scatter plot. Well, here you've got in the plane, so you've got the surface and all that stuff. The accuracy of the function as a prediction for y depends on two quantities, reducible error and irreducible error. Okay, there's a whole chapter that we could talk about what these things are, and if you go on and you do independent work in structural equation modeling and stuff like that, you're usually talking about the error term. I know that sounds weird, but you're talking about the error term more than you'll ever imagine in some of those methodologies. And if you go into psychometrics, if you do further work in psychometrics, you're talking about the error even more. So we know that somebody's score, right, is made up of a true score plus an error. The big thing is to understand why there's error. So the book makes two distinctions, reducible error and irreducible error. Well, when can you have irreducible error? Well, irreducible error in this context is considered error that is going to happen, right? It's going to happen even after you've tried to take care of error that you can control, okay? So maybe you can get a function where you're predicting values. Maybe you can get a function where you're predicting values, but observed minus predicted, but you're still going to have this error you just can't control. Now, what is this, right? What is the error you can't control? Well, again, that's a pretty big thing. And the book just talks about it rather simplistically, just saying, well, it's just error that you cannot ever get rid of, right? You just can't ever get rid of the error. I would disagree with that a little bit, because theoretically you can say, no, we should be able to get rid of that error. If we know all about the function, right? If we know all about the function, eventually that error should go to zero, right? It should go to zero, at least in theory. On the opposite flip of the coin, you can say that we can never get rid of it. Both ways of looking at it, strangely enough, are correct. Theoretically, you can always get rid of it at some point, or maybe it's always there. Now, if we brought in a physicist who looks at quantum theory and all that stuff, they may disagree with what I said. They may say, no, this is irreducible. There's actually true error and variability in observations. And some of that stuff, they're actually looking at physics, saying there's actually like real chance. Okay, there's actually real chance that occurs. It's not actually simply eliminating, all the systematic components so you can find those things. There's actually real chance. I remember looking at a study recently about the, what causes cancer. Can you predict cancer? How do we know some people get cancer, some people don't? And I didn't look at it very much, but I know the headline kind of said, I think it was something like 2/3 of cancers are unpredictable. I think it was 2/3. Don't quote me on that. But a fairly high proportion of cancers were simply unpredictable. So even if you had a good diet, even if you had genetics that will not promote you to getting cancer and things, it's just, boy, those cells, right? Just, one day your cell just decides it's going to do something different. And they were talking like that. So in that sense, you can almost think of that as that's irreducible. It's just, there's nothing you can do about it. Now, of course, the study was criticized by people who are saying, no, lifestyle matters a lot more and things like that. But the point is that there may be some irreducible error. Now, in psychometrics, that's a pretty big thing too, because we want to study how much error is there involved in observations, measurement error. You can think of it loosely like that as well. Is there error in measurement? When you take measurements, how much measurement error are you getting? If you measure on one instance and then you measure on another instance, maybe the scores are different simply because of the process of measuring. Kind of like sampling error, right? Remember sampling error. What's sampling error? Sampling error is error due to sampling, right? It's error due to the process of taking different samples, which all of that we can also call under the name of chance, right? Under the name of chance. These are imperfect words to describe these things, but we do the best we can. So you can look at it saying there's some error. You're just never going to get rid of it. But the reducible error, you will be able to. The other idea is inference. We want to make inferences. So which predictors are associated with the response? And that's a general question. That's not simply a regression question that exists in different procedures. It's a very general thing. And then we want to make predictions of future observations. Okay, so these things, we've all seen these before. What's the relationship between the response and the predictor? Is it adequately described by a linear equation, or is the relationship more complicated? Okay. Now, you can answer that right away because you can say, of course, it's more complicated. Linear equations are imperfect for every situation. 99% of situations, linear equations are not going to fit your data. So why do we use them? Well, we got to talk about that in terms of variance versus bias. But the complicated ones are sometimes it gets so complicated that, again, you have this black box idea that we really don't know what the algorithm is really getting at. But we just know that it's predicting that if you use your credit card 3 times in a row, you may be one of those people trying to commit fraud. So that's why it cuts off your credit card and you have to call the bank and you have to say, no, it's really me. I just made 3 purchases because I'm spending a lot of money. Okay, so the company that in business, sometimes the company is not interested in understanding the relationship between individual predictors and response, so they don't care about that black box. They just say, just tell us what works, and we'll go from there. And again, that's a theme that's kind of coming up a little bit more and more, especially with the big data, especially with business applications. But as a scientist, you usually care, right? You care why cognitive behavioral therapy works for some people and it doesn't for others. You care, or at least you should care. You care about that function. What is it about this treatment that works for some people versus none? Why do some people recover from depression? Why do some people have psychological disorders and some don't? Why do some people have schizophrenia, right? We care. We care about the function. We don't just care about being able to predict. We care about the function. So you're leaning as a scientist on explanation. You want to predict, but you want to explain too. Quick example here, they talk about what effect will changing the price of a product have on sales. Well, directional issues, right? And big stuff, it's not minor stuff, right? That's not minor stuff. What effect yeah, I don't know what effect means in the context unless you actually have like an experiment, unless you have controls and stuff like that, right? No regression equation and no statistical learning method will actually tell you what has an effect on something else. Okay, and those are really important things because all they're doing is kind of working an algorithm and moving data around. It doesn't necessarily tell you what influences something else. Okay, so we kind of sometimes we joke that within the computer science atmosphere, sometimes people are kind of like obsessed with the compute and say, well, we just compute more. We just need more computing power. That's fine to have computing power, but it's not going to tell you if COVID treatments work. That for that you're going to need experimental design. So the design first, and then the computing application after, from a scientific point of view. Also, we're going to see that pattern recognition. You can detect patterns in data, but it's not going to necessarily tell you what's causing those patterns. It's not going to tell you very much more than it can identify patterns. We'll look at an example here in cluster analysis. So what's interesting is many of these problems we're going to see. I mean, sometimes, I mean, um, I teach statistics and methodology, and I'm the first, right? And this is going to surprise some people. They say, "Hey, anything that has statistics in it, Dan's going to be like, wow, I love statistics." Okay. Well, the problem is that should be a T. The problem is that when you use stats, um, you want to make sure you're using it in a way that clarifies your data. You're using it for your data, so that you can use statistics on something, but you always got to remember that it's the empirical observations you're most interested in. You don't want to um, um, look at statistical artifacts and things like that, and that's easy to happen, especially with law research. Okay, so how much extra will a house be worth if it has a view of the river? Inference problem, predictions, etc., like that. Back to my point here is there's sometimes you're actually better off not using statistics in some environment, or using like minimal statistics to draw explanations. What's most important is always what the project is underneath, and that usually comes down to design issues. So I'm going to sometimes say that the research methods course is actually really more important in that sense than these statistical learning methods, because these statistical learning methods are kind of arising in non-experimental context. As we're going to see, there's not much experimental context in this book. So you have to use these methods and remember that you're still trying to make a scientific claim. Okay, that's important. So how do we estimate it? Well, we have this distinction between training data and then we have test data. Okay, now training data, again, verbiage, right? Training data sounds, what the heck is training data? Well, it's what we've done in like 521. And if you haven't taken that course, it's what you've done before. You fit a model to data. You're training the data. What the heck does that mean? Why train the data, right? Say, well, why train? It used to be just analyzing the data. Now it's training the data. Well, we got to talk about what train means. I can't explain it now what it means, but later on, you're going to see exactly what it means to train the data. Okay, what's the train the model rather on the data? And it sounds complicated, sounds sophisticated, but again, we want to break it down to its element components and say, you know what? What's going on is just this. Okay. Same thing with machine learning. What's machine learning? It's all the vogue right now, right? People using machine learning. That's great. That's no problem. But we want to break it down to saying machine learning is actually doing this. And once you see what it's actually doing, then it demystifies what the term is, how it's being not misrepresented. It's not being misrepresented, but some of those terms are also part of the zeitgeist, right? The spirit of the times. And you'll see that some of the things that we call machine learning and we name by these certain verbiage is actually very similar to things that some people were doing like 100 years ago and 150 years ago, but it was called different things. Now, that's not to say machine learning doesn't have a whole bunch of contributions to it, but you have to understand, where's the machine? And that's a reasonable question. Where's the machine? If it's called machine learning, where's the machine? You can distinguish between parametric versus non-parametric procedures. Okay, so there's parametric versus non-parametric. What do parametric procedures do? Well, they make assumptions about the parametric population, the family that you're dealing with. If you look at the typical regression model, well, we know that that has certain assumptions with it, right? And in previous courses, you've looked at there has to be linearity. The errors have to be well-shaped and things like that. They can't have variance problems and stuff like that. So it's making parametric assumptions about the population. Fit, train. So again, you fit or train the model. The statistical learning language suggests you train the model. Basically the same thing as fitting it. What does that mean in both cases? What does that mean? Well, they actually tell you in the next sentence, because they say, in the case of the linear model, we need to estimate the parameters. That doesn't sound very much like training. Estimating parameters doesn't seem like training. So there must be more to it than that. And there is a little bit, and we're going to see it. Least squares, we're all okay with that. We know what least squares is. The model-based approach is the parametric approach, and we know that that makes assumptions about the population, and we're all good there. Now, we have this idea of flexibility. Okay, we want to choose models for different situations, and we have to introduce this variable of flexibility. Some models are more flexible than other models. So what does that mean exactly? Well, flexible models usually will have more parameters. Okay, so the number of parameters increase in the flexible model. What does that mean? Well, we can think of it in terms of multiple regression. You can have several predictors, right? So predictor 1, 2, 3, 4, 5, 6, 7. That has a lot of flexibility to it because it's involving a lot of parameters. A little bit more flexible than a simpler linear regression model. That's the way to think of it in terms of linear regression. We'll see in the next page and pretty soon how different methods that we'll look at can be placed on the spectrum of flexibility. Overfitting is an issue that we're going to have to talk about. And overfitting, people have been overfitting models for years, and overfitting is a general concept. Let me give you the example of what exactly overfitting means from a very, very conceptual point of view. So you're a psychological theorist, and you have psychoanalysis as your theory, or behaviorist, or whatever other theory, humanistic psychologist, and you observe the behavior of your client. Okay, you observe the behavior of your client. Well, you try to have a theory about that client, right? And it helps you make predictions. What will happen to the client? How will they recover from what's troubling them? Will they, what will happen? What's that long-term prediction? If you overfit the data, you won't be able to generalize to new data. Okay, you won't be able to generalize new data. So if you observe the particulars of your client, and you say, you know what? That person has 2 cups of coffee in the morning. I'm looking at my coffee right now. That's where I get my examples. That's where my inspiration comes from. So if you say, well, that person has 2 cups of coffee in the morning, that must have something to do with what they're going through. And you try to fit stuff like that to the data, you're going to find, and maybe there's actually a little bit of truth to that, because maybe the caffeine is having an adverse effect on them or something like that. But if you get too particular like that, you will not be able to generalize your theory to new observations. In other words, that's not going to be true of the next client. Okay? So if you specify the theory too much, you're going to be overfitting the data, because you're not going to be able to make predictions to new people. Now, a humanistic psychologist like Carl Rogers, that's not going to bother him, because he's going to say my population is of size 1. And say, I'm interested in that person and the amount of coffee they're drinking. I don't care about generalizing to new people. So maybe that's fine. But in other cases, you definitely do care about that. Example of overfitting from a statistical point of view. What's going on with this data? There, fits perfectly. You'll never do it, right? You never do something like that unless you're dealing with actual things that are very, very precisely measured. Again, I remind everybody, the measurement problem is fundamental. It's not, statistics won't save the measurement problem. What is being measured is most important. The statistics come after. But if I look at this and I say, you know what, this is based on physical objects, right? Observed in the like the collider or something like that, and it's very precise. Maybe this is an actual good representation of the function. Maybe this is actually true. But if you take a lot of other data, like a lot of social data, which is very filled with the error term, and you get data like this, the problem is if you fit this function to it, if you connect the dots, right? Like your 3-year-old connecting the dots, what's the problem? Right? What's the problem? You've overfit it. Why? Why not overfit it? Boy, this fits a lot better than this sloppy line. Why not fit it exactly? Well, the problem is that if you do it this way, if you connect the dots, try applying that to a new sample. It's never going to work, right? It's never going to work. So you fit it very precisely to this data, but if you apply it to a new data set, that function's not going to hold. Again, unless you're dealing with very, very precise elements, then maybe it will. So the overfitting idea has to be context dependent on the research area that you're dealing with. It's not just something that you can just blame on the statistical method. You have to actually look at the material you're dealing with to kind of get an idea of whether you're overfitting or not. But overfitting is generally not a good thing. Underfitting is not necessarily good too, but I'll tell you, it's probably the safer approach. Okay, when do we underfit? Let me put it up here. I'll give you an example of underfitting. What's underfitting here? Can you guess what I'm going to draw? That's underfitting, right? That's a horrible fit, right? That's an awful fit to the data, relatively speaking. This is a much better fit. But we underfit a little bit so we can generalize to the next data. Okay, you see that. Now, what's the principle here? The principle is this. Look, that line is kind of like, in statistics, a theory. Can you see the underfitting versus overfitting idea from those of you in psychology and maybe other fields in terms of your theoretical predictions? So where's the underfitting in psychological theory? Well, maybe the underfitting, and I'm not well versed in psychoanalysis, so I'm trying my best. You know, the id, superego, and ego. Well, maybe that's actually an underfit, because that's kind of general, right? And you say, well, that's due to your ego, or that's due to your superego. It's like, that's pretty vague. We can get more specific on any one particular person. But Freud underfits a little bit. Why? Because he wants to generalize that to new people. Okay, you get that idea. That's the idea of underfitting and overfitting. And it's true of statistical modeling, but it's also true in terms of, you know, just every theory that you come up with, right? It's almost like the origin of the species theory. That's kind of underfit to a great extent. So there's a balance between overfitting and underfitting. And if you have to choose one or the other, and it's something that comes up at dissertations, right? It's like, you know, your theory is a little bit too particular. Do you know if that's going to generalize? And sometimes it does, and sometimes it doesn't. But beware of doing things like this, where you say, there, hey, I'm going to fit this really good with a different curve other than linear. That's overfitting. So you underfit. Now at the same time, if you have data like this, and you say, well, I don't know, I heard Dan say that like overfitting is a bad thing, so let me just do this. There, that'll take care of that. Well, that's underfitting. You say, well, you haven't even used the data, you've underfit. Okay, so this idea is really important, and you'll see that again. It's a scientific idea. Many of these things come from like notions of science too. They're not like pure mathematical objects, because much of the statistical mathematical methodology was actually motivated by scientific problem. So you think of it in terms of that spectrum, overfitting, underfitting. Usually you want to underfit. As a scientist, you want to underfit a little bit. Again, the idea of overfitting is very popular in machine learning and data science, but it's existed forever, which is one of those terms. I heard a student once say that they were talking about overfitting, and they thought it was particular to machine learning, or they thought it was particular to a certain methodology, which isn't true at all. That's been that the concept has been in statistics forever, and it's been even larger in science, as we've been talking about. Non-parametric methods, okay, do not make explicit assumptions about the functional form of f. Okay, they do not make explicit assumptions. And this is an area where people are kind of liking these days because they're getting tired of statistical theory, right? They're just getting tired of having to know the assumptions of their method and stuff like that. They're saying, let the data speak, right? Like in a deep voice, like let the data speak. Well, that's fine, but you're not going to necessarily get as precise mathematical modeling if you can make some assumptions and zero in a little bit. But oftentimes, like in the big business applications with big data, we may just say, you know what, we don't care about the assumptions, we're going to use a different method. Comes with some weaknesses. Often you'll need a very large number of observations. It's a little bit different than doing non-parametric statistics that we're probably all familiar with, like doing like a Kruskal-Wallis test and stuff like that based on ranks. Those often require, you can have small numbers of subjects. But for these big non-parametric methodologies in statistical learning, often you require a bigger N. They talk about a thin plate spline here. This function, we'll talk about these splines later in the course, or somebody will. This actually fits it pretty closely, but it's an example of might be actually overfitting a little bit because it's fitting a little bit too closely. Different levels of smoothness. Again, talk about splines. You can adjust the level of smoothness of the spline, but again, if you fit it too perfectly, right, then you may be overfitting the data. So we've talked about this, how much bad theory, new data is an undesirable situation because the fit obtained will not yield accurate estimates of the response on new observations that were not part of the original training data set. So that's important. You're going to train the data and then you're going to test it. Bad theory, new data. 2 cups of coffee has something to do with cognitive decline. Nah, it's only true for that person because they're sensitive to caffeine. Next person, no, it's not going to work at all. Well, general poor nutrition has everything to do with cognitive decline. Hey, that actually might work on new data, right? Maybe that's true in general. Notice as we go to the general, right? As we go to these general themes, you lose specificity of the information. It's actually not quite as exciting because you can say, yeah, all humans breathe. Okay, well, that's not very specific, but it's safe, right? It's safe, right? What's an example of underfitting? Guess the mean. The mean's a very safe way of underfitting. Just guess the average. You're going to underfit, but it's not going to be terribly exciting. Okay. So we have to look at those issues as we move forward. The trade-off between prediction accuracy and model interpretability. Here's the chart I think I was referring to earlier when I said these things are put on a spectrum of flexibility. So as flexibility increases, and by flexibility, sometimes we mean the number of parameters, the complexity of the situation. We're going to have high flexibility. Interpretability is over here. So you have interpretability, subset selection and regression, things like lasso regression, which we'll talk about, least squares. Those are not very flexible, but they're high on interpretability. Like linear equations are pretty interpretable. And in some contexts, that's a really good thing. Lasso regression, we're going to see as a model selection technique that tries to drive some of your predictors out of the equation. It literally tries to get them to zero. Right, it's going to drive them out. It's going to go, that predictor X2, let's try to get rid of it and get that weight to zero. And in that sense, it could actually help you identify the best model. of what you're dealing with. But these here, they're going to be pretty interpretable. You're going to know because you're going to look at if lasso regression is trying to drive 1 year predictors to 0, then it's saying X1 and X2 in a sense, and we've got to say in a sense here because we haven't unpacked this fully, maybe X1 and X2 are actually more important than X3 and X4. Because X3 and X4 through the lasso regression algorithm, which we'll talk about, has driven X3 and X4 to 0. So it's kind of bringing the better predictors to the surface, and that's a relatively recent methodology, and it's actually very popular in statistics. Can also help deal with situations of collinearity as well. You've got other things here. Bagging, boosting sounds complicated. We're going to see what those are about. Support vector machines. Those are relatively high on flexibility, low on interpretability. So support vector machines especially, we're going to see it's a classification problem where you make a classification between classes, but you may not actually get that much insight into why it's classifying the way it is. Kind of like the credit card fraud, right? They just called me. They said, you're using your credit card too much, or, and it's like, they only know what I'm shopping for. Or they only know that what I'm doing with the credit card, but it's a general thing. All they know is the bell went off because you used it 3 times in a row. The support vector machine did that, right? It classified you as a high risk person because of that behavior, but it doesn't get into particulars as to what predicts the response other than you used your credit card 3 times, right? A more interpretable methodology, more interpretable, would be what exactly were you shopping for? So maybe a more interpretable method would be able to say something like this. Well, we saw you shopping on Amazon and you bought 3 things, and you bought a computer for $1,000, and then you bought something else, you bought something else. We put that information into our model, so it's very interpretable. So we didn't call you, or we didn't cancel your credit card. We didn't lock it. You see the difference? In that case, it's very interpretable. It's very specific. And that's why linear models and things like that are often used in scientific investigation, especially precise mathematical modeling, because you actually want to know the process. Tolman, with the cognitive map of the rats, actually wants to know why, explain why, whereas in other cases may not care why. Okay, so a little bit of a distinction there in terms of that interpretability. Now, the support vector machine, you may not know why exactly, because it involves some things that kind of don't outline the theoretical issues as much as these techniques. A big mistake would be to say that these are always better than these. Okay, not necessarily the case, as we'll see. Why would we ever want to use a more restrictive? I think we just talked about that. Maybe it's more restrictive. Sometimes they work better and they're easier to understand. You can actually get more theoretical insight. Remember, parsimony is the key. If you can explain things with one experiment using a t-test, that's excellent science. The COVID vaccine, I guarantee you, is going to be done on the t-test. It's going to be done on something like that. Mean differences. How many people survived? How many people didn't? Stuff like that. Now, there may be some other modeling involved, but the biggest scientific questions are, if you have a good design for it, are actually relatively simple statistically. Sometimes I like to say that the more complicated statistics you need, the more there's less there. And there's a lot of truth to that. When you need like 1 billion parameters to model something, does that mean you have a handle on it? Or does that mean it's almost like it's being covered up by too much statistics? So simple is always better in that regard. It's almost like if you don't even need this book and you can do science without it, you're actually more advanced scientifically in a sense than if you have to use a lot of statistics. Now that will never happen. That's why we need the statistical methodology, but you kind of get the feel for that. Simple is better. Occam's razor. Black box, talked about that. We talked about the lasso. A few other models we'll talk about later. We talked about these a little bit. Supervised versus unsupervised learning. Okay, what's the difference between the two? This is kind of, again, more language, right? We already know what supervised learning is. because we've done it. And I'm going to generalize this to things that are not mentioned in the book because they have the same conceptual notion to them. In a very strong sense, analysis of variance is a supervised learning technique. Okay? T-test is a supervised learning technique. Why? Because if I draw my function statement, I have my y and my x here. When we do a t-test, we've identified the grouping structure. This group and this group. Our theory is here. Right? Our theory is here. There's our response variable, but we've already had a theory as to how they're going to group. Right? When you specify males versus females, or low drug dose versus high, control versus experimental, you're specifying a theory. That, in a sense, can be regarded as supervised learning. I don't like the term. I find the term supervised. Nobody's supervising it. It used to just be called having a grouping structure pre-prescribed to it, right? A hypothesized grouping structure. But in the lingo, that would be considered supervised. Regression, supervised, right? It's because you're using X to predict Y. So that would be supervised as well. Unsupervised is, in this case, you don't have a grouping structure. You don't know what the grouping structure is. So in other words, in many unsupervised learning techniques, all you really have is Y. All you have is this, a whole set of data. So what you're going to do is you're going to set the algorithm free on it to try to learn in an unsupervised way. The algorithm is going to try to find patterns for you or other associations. Again, not necessarily any experimental controls, that's a separate issue. It's just going to find patterns in the data. Now, if we talked about these distinctions long enough, we would see that they're kind of artificial to a large extent. Why? Because when we do PCA and factor analysis later, we're going to see that there's really no unsupervised learning. It's kind of a misnomer because when you do PCA, like we talked about a little bit last time, when you do factor analysis and things like that, you're always specifying things in the model to some degree. You're always, this joke I like to say, nobody arrives at a computer, sits in front of data and says, data speak, right? It just doesn't happen that way. The algorithm you apply, the choice of algorithm, the parameters you set a priori for the algorithm, the number of clusters that you hypothesize and setting the cluster number, as we're going to see, the number of factors that you ask SPSS or R to pull out, sounds a lot supervised because you're the one saying, let's try 3 clusters. Well, why 3? Well, you're supervising the method, even though it'll still be called unsupervised. So again, you know, the statistical learning environment, they like to make these distinctions, but I mean, we start to break those down and it becomes a little bit like a trivial discussion, but we don't want to be confused by the language. Half the part of learning new statistical methods is unpacking the language and realizing it's something you've already done or something very, very similar. It's amazing how those things happen. And you'll say, oh, it's just that. Then why are they calling it something else? Well, there's reasons for it, but there's also, you know, something sound nice, right? So we have to unpack it. Got to get back to the bare bones of what the heck is going on. So no response variable. You just have data that's unsupervised. Okay. Cluster idea. There's groups. There's one group. There's another group. There's another group. Set the algorithm free and try to find the grouping structure. Maybe it finds one group here, one here. It's not going to do it perfectly here because there's overlap. But again, if you set the cluster number, which we're going to have to do when we get the cluster analysis, at least for some techniques, it sounds a lot supervised to some extent, but it would still be considered unsupervised in the language. Cluster analysis, as we just talked about, is an algorithm that's going to try to find those relations in the data. It's try to find the grouping structure, right? Maybe females, males, and trying to distinguish between the two species, trying to distinguish between the two, 3 species, or something like that. Now, cluster analysis is a technique that researchers sometimes like to use. Market segmentation is important. They want to know what types of customers are buying stuff on Amazon, right? So that when you buy something on Amazon, they can They know the next ad to give you, right? And I mean, it sounds sophisticated, and they go, wow, this must be like artificial intelligence. Look, I bought a computer and now it's telling me, hey, which type of mouse pad would you want the next time I logged on? It's not that complicated, really, right? It sounds artificial intelligence. Wow, the machine is smart. Well, we have to unpack what the machine is doing, and we're going to see, yeah, it's not actually that mysterious, right? It's not actually that mysterious. Interestingly enough, that in cluster analysis doesn't know what a cluster is, right? I'm not being silly. It doesn't know what a cluster is. It cannot define what a cluster is. So we have to propose definitions for what a cluster is. We'll return to that point when we get there. It's an important point because you may find clusters in your data, and then you may prescribe causes to those clusters, and your causes could be not correct. And you may not have the methodological design for it for making those conclusions. So more to come on cluster analysis, but you're looking for group structure in general for that. More stuff here on more supervised. You can read that over. Semi-supervised is something we usually don't have to worry about. Regression versus classification problems. When we have regression, we know we have a continuous response, usually a continuous predictor, although you can put it into categories and you can do dummy variable coding and things like that. Classification is usually when we have a binary response or multiple categories. We'll be looking primarily at the binary situation. So you have like Y has two categories, 0, 1. You're trying to predict into the categories. Very similar to the idea of regression, but it has the binary response. You've got to treat those things differently if it's binary. You can't use classical techniques if you have K different classes. You have to use things like logistic regression, discriminant analysis. Talk about K nearest neighbors and boosting and stuff as we go. You can code your predictors, and you can generalize that to like regression models. So we know that. We know that you can code predictors and you can treat like ANOVA as a subset of regression. What's the best method? Well, there's no one method that dominates all others. So this is a question sometimes that's asked a lot is, which method do I use? Well, it's important, right? Which method do I use? Well, there's a few methods you could use. And, you know, people don't like to hear this, like, well, which one do I use? Which one is the correct method? Well, you may want to define the correct method on which one works best on your data. What does it mean to say it works best? Difficult to untangle because maybe you're interested only if it makes good classifications. Can we predict credit card fraud? If we can, this method works best for this data. Can I predict what the rat's going to do, and can I understand rat behavior? Well, method 1 maybe doesn't explain as much variance as method 2, but I understand more of what the rat might be doing. That has to play a role as well, right? So that's why some of those less flexible approaches actually can offer a little bit more insight into what may be going on, even if they're a little bit simpler than the more complex methodologies. So the best method has to be determined by multiple criteria. It can't just be like what the big business wants to know. Tell us who's going to default on the loan, right? As a scientist, you may have slightly different criteria. It may not always even be about maximizing R squared. So it becomes a little bit complicated and a little bit more involved than kind of what they're describing here. But just recognize there's different methods that can be used. Now, in today's environment, sometimes people will try a whole bunch of different methods if they're only interested in prediction. And there's nothing wrong with that. You can try different methods. But if you're a scientist who has a hypothesis, which you should have, you have a hypothesis, you don't want to be on the fishing expedition. So you see that a lot of the movement in like computer science and getting patterns from data, those are fishing expeditions. But no one pretends like they're not, right? Just tell us what kind of, you know, when you do like a cluster analysis, tell us what type of people are buying on Amazon versus not buying on Amazon. Amazon not buying on Amazon. Well, that's a fishing expedition. There's no theory necessary there. You're just doing a fishing expedition. But after the fishing expedition is over, you might want to understand more about those people. That's where theory comes in. Why is theory important? Because maybe you actually want to just understand. Understanding is important, right? Just going, those people are more like this than that. That's interesting. Or you may want to predict future responses, and the theory helps you predict the future responses. Okay. So there's two sides to it here a little bit, but we definitely don't want to get like atheoretical and just throw the algorithm on it and see if it works, right? We want to usually understand the process. And like as a clinical psychologist, especially, you probably want to understand what's going on, right, with your clients rather than just predict whether they're going to respond to treatment or not. Because imagine if you're explaining to a client, right, they're saying, why should I do this treatment? You say, I don't know, because it works. Well, why does it work? I don't know. I did the support vector machine on it. Just works, right? That's okay for like a day or two, but after you're actually going to want to explain the process. And if you say, well, it works because we think this is the reason why it works. I just thought of a really good example of that from the medical area, psychiatric medication. That's actually a really powerful example, right? Because we know that many psychotropic drugs, we don't know their long-term effects. I remember learning about them when I was in graduate school a little bit, and some of you may know more about psychotropic drugs than myself, but because maybe you studied it more. But if you look at the drugs, sometimes they work. The person feels better, or the depressive symptoms go down. But why? Maybe it doesn't matter right now because they got better, but it will matter in 30 years from now when we realize the long-term effects of taking that. So, but if you understand the etiology and the explanation of what's happening now, you can say, okay, this is actually going to be a bad thing in 20 years because we actually know that you're going to habituate to the drug or it's going to alter your neuronal chemistry, and that's not a good thing. So maybe the explanation is important. So beware of that, which from the clinical side, depending on your clinical stance, is one reason why sometimes psychologists aren't always in favor of psychiatrists, right? Because maybe psychiatrists are more likely to say, oh, you're suffering from depression. Oh, there's some medication. You'll feel better. Well, of course you'll feel better. The medication is altering your neuronal chemistry, but is it getting you anywhere, right? Are you actually learning anything from it? Or is it just a quick fix? So maybe you want more of the process, and the process is in the theory and finding out what's going on behind the mechanism, not just applying the mechanism. Okay. Same can be said for statistical theory as well. You apply a statistical method, but if you don't know what the statistical method is doing, well, then you really don't know if what you're getting is actually valid or meaningful or if it generalizes or anything like that. That's why the theory has to come first from the scientific perspective. We want to minimize mean squared error. We've talked about this in regression, and you've all seen that. Observe minus the predicted values of the function. That's one way of kind of assessing the quality of fit. How well does it fit, right? Low mean squared error, high mean squared error. Training MSE versus test data. Let's take a break in a second, but I just want to make this distinction before we do. The training MSE is the mean squared error based on the data you're fitting the model to. So when you fit it to those like 100 observations, that's called the training MSE. The test data is what you're actually interested in validating the model on. So again, we have this idea of overfitting, underfitting, and how well things generalize. You can get a low training MSE, which is nice, but the MSE may actually rise on the test data. And what these authors are excellent at talking about, very, very good writers, is it's actually on the test data that you're most interested in. Now, this is going to be new to probably all of us because we're used to fitting the model on the training data and making a conclusion from that. So we fit it on the training data and we say, hey, the model fits well. Well, what's the question your thesis committee is going to ask you? Right? They're going to say, it fits on the data you fit, but what's going to happen if you try it on new data? What happens if you try the function on new information? Right? There's the estimated function. What if you try this on new information? Well, I don't know if it's going to work out so good. Well, if you've underfit a little bit, you're probably going to work out better than if you've overfit. So it's the test data that we're actually interested in, the previously unseen data that we actually want to know the performance. And that comes up in scientific investigation, in general discussions of cross-validation under that theme, right? Well, have you cross-validated that? Or are you making too much about the 2 cups of coffee? Right? Have you cross-validated that? I mean, or is your 3-year-old connecting the dots? You see the analogy. Have you tested the theory? Freud had to test his theory, right? Skinner had to test the theory. Look, the pigeon behavior does this. Well, that's on one pigeon. Maybe that's just characteristic of that pigeon. Maybe all you're seeing is error. That's an E, an epsilon. Test it on another pigeon. Does the next pigeon do the same thing? Well, not quite, but nearly so. Well, maybe you've got something, right? Getting good theory is really hard. Future patience. You want to look at the future. The test MSE is what you really want to minimize. You want the lowest training MSE. You want the lowest test MSE. The test MSE is what's most important. So that's what they're saying here. Get the lowest test MSE as opposed to the training MSE. Now, you want both. Both are nice, but this is the one that they're arguing matters the most. Again, this is a new component to much of the modeling that many of you have done, because we usually don't talk about that in introductory classical courses. We don't talk about the difference between the train versus the test. And it comes up sometimes at dissertation defenses where people say, my model fits great, but then you get the quantitative person saying, yeah, but you haven't put it on test data, so we don't know. Now here's the bummer. The bummer is that oftentimes we don't have test data available. Right? We just don't have it available. Maybe you have to fit your model on 300 observations and it's expensive. You don't have test data. So we might have to come up with some methods that help us estimate that test error rate without actually testing it on new data. And we'll look at those methods as well. Okay. But sometimes if you have a big sample, you can do sample splitting. So maybe you got 1,000 observations, split it into two groups, and see what you have in terms of applying the model to one half and then testing it on the other, which is a really nice thing to do. Otherwise, you could be capitalizing on a whole bunch of error. Here's an example very quickly, and then we need a break, is the curves fit to data. There's a least squares regression in that kind of beige curve, and then you've got different functional forms here. I get right to the point is we see as the flexibility of the method increases, so the number of parameters, remember that linear equation is not very flexible, but the other ones start to be more flexible. What happens to the train MSE? Well, not surprisingly, okay, and this is gonna like blow your socks off, right? Mean squared error goes down. Well, that makes sense because it's more flexible, connecting the dots by analogy. Hey, if you're connecting the dots, ask your 3-year-old, how'd it go? Did you make much error in connecting the dots? Say, no, I didn't make any error at all. Wow, that's awesome. You're highly flexible because you actually join the points. What's your error rate? Low, right? Your mean square error in connecting the dots is very, very low. The more dots you connect. The more dots you connect, very low train MSE. But look what happens. And again, I said it's going to blow your socks off, and it will, right? Because look at this. Look at this. Okay, you're looking at that, you're going, okay, that kind of makes sense. And that's no problem. If I got a low flexibility model, hey, they're both going down. I got no problem. But then what happens? Look what happens. Flexibility increases. The train MSE goes down. Look at what happens to the test MSE. Now, if you understand the difference between the test MSE and the training idea and the flexibility, this makes sense. You're like, of course it should, right? Of course it should. Why? Because this method has been trained on patterns inherent in that data. It's been overfit. It's too flexible. You fit it too precisely. 2 cups and 2/3 coffee with half a sugar, 2.8 creamers is associated with the depressive symptoms of the client. Oh my goodness. Too flexible, right? You've got too many parameters. Too many parameters. You've trained it really well, but as soon as you test that on the next client, on the next empirical observation, the next client comes in and say, I know what your problem is. The 2.8 creamers. It's a silly example, but you get the point. If you go to 2 creamers, you'll be fine. Wait a minute. Look at all the air you're getting. There's the perfect example for that idea of the train versus the test. So we see that they diverge. And again, we haven't seen this stuff before, many of you, in terms of train versus test, but now it becomes a regular idea, training versus testing. And again, we often don't have the data. Sometimes it doesn't matter, right? Look, if you're low in flexibility, your model's relatively low in flexibility, you actually don't need it, right? So if you're fitting the linear regression with 2 parameters, 3 parameters, it doesn't really matter anyways. You're fine. But if you're doing a really complex thing, you got to be aware of that. So, the regressions the multiple regressions and stuff like that, you're usually okay because they're both kind of decreasing. So our intuition there is actually usually correct. We're actually saying, well, we're fine. But as this starts to change, you have to be aware of that. So your supervisors may say, well, the training data is fine, but what about the test data? It's something you need to look out for. Okay, so they appear to be closely related, but they're not, as we saw in the graph, and that's what these authors do really, really well, right? Test error may not be equal to the train. Might want to smooth too much smoothing, right? You make it too smooth while you're overfitting the data, and it's going to be a disaster if you try to generalize that. Degrees of freedom, another way of looking at it, describes the flexibility of a curve. So, in the linear model with A and B, has a couple degrees of freedom, but as it becomes more complex, the number of degrees of freedom increase. So we have to be aware of that. That may ring a bell a little bit with some of you in terms of the adjusted R squared idea, right? Adjusted R squared. If you're going to fit a lot, then you have to get punished for it in that sense, right? You're going to fit a lot of parameters, R squared is going to go up. Our adjusted R squared isn't impressed, because adjusted R squared says, I know what you're doing. You're fitting everything under the sun, right? You're on a fishing expedition. You're going to put every predictor in there that you can, and then you're going to say your model is impressive. Well, the adjusted R squared spirit is saying, I don't think so. You're fitting a lot of parameters for nothing, and you're not getting the bang for the buck. We're going to punish you, and it's related to that. You can think of it as being related to the graph we just saw. It's not quite the same, but in the same kind of idea. Overfitting, I think we've talked about that enough. Why is this person unhappy? When a given method yields a small training, but a large test MSE, we are said to be overfitting, and we've just talked about that. Large test MSE is bad, even though the training, right? There's the 3.8 creamers, but it's going to be a disaster on the next client. You're not going to be able to predict anything. So, you want to underfit a little bit if possible, and it makes things a little bit better. Okay, I think let's take a quick break, and we will continue to talk about this, especially with this bias variance trade-off, which is a really, really important theme of the book and of the course. So take a quick break, and we'll be right back.